Between your end stations and your access layer switches, you'll typically use the UTP cabling with the RJ45 connectors because it is your least expensive option. However, between your switches and from switches to routers, you'll probably end up using some type of fiber optic cabling. Why? Because it's less susceptible to electromagnetic interference as well as other types of interference. In addition to that, you will get higher throughput by using your optical cables. So when you are dealing with optical cables, you are dealing with something that is very fragile because in the middle of your optical cable, you have a core that is made of glass or silica. And the purpose of that core is to transmit the optical signals, so the light through it. And we then have to wrap that particular core up in what is known as a cladding. So what is the cladding all about? Well, the cladding is designed to make sure that the light stays inside the core. That's the whole point of the cladding. However, if the light beam that is going through the core is not at the correct angles, then what will happen is the light will leak out of the core into the cladding. So what we want to do is we want to make sure that when we are using optical cables, we are providing what is known as a total internal reflection. So what do I mean by that? Well, look at the two different types of fiber we have here, a multi-mode fiber and a single mode fiber. With the multi-mode fiber, notice how we have the light beam going up, being reflected back in, reflected, 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 and so on and so forth. Same thing with single mode fiber, reflected back in, so on and so forth. If we come with the light source at too much of an angle, then there is a high probability that we won't get that total internal reflection inside the core. So when you are deploying your single mode fiber or your multi-mode fiber, you want to make sure that you don't bend your cable more than what is specified by the manufacturer. Because if you bend the cable more than what is specified by the manufacturer, then you are really, in the end, at those bends, changing the angle that the light will hit the cladding. So if the light hits the cladding at more than our critical angle, then what that means is that light is going to lead into the cladding, and when the light leaks into the cladding, it doesn't completely get reflected back into the core. So now we have light leaking out. That's going to affect our signal to the point where maybe our signal can't travel as far, or we have data loss because data is leaking into our cladding. So we have these N1 and N2 values here, which are going to be specified by the manufacturer of the cabling. And based on these N1 and N2 values and using your scientific calculator, you'll be able to figure out what is your optimal values and optimal bends that you can have with your fiber optic cable to make sure that you don't have light leaking out of the core into the cladding. One thing I want you to notice here is that the core is of different size here with single mode fiber and multi-mode fiber. So with single mode fiber, we have a much, much smaller core, and we are typically going to end up using laser as our light source. What that means is that with the smaller core and utilizing lasers, we can have very, very long runs of fiber optic cables, extremely long runs. We're talking about kilometers and miles when it comes to deploying the single mode fiber. But with multi-mode fiber, we can have multiple sources of information flowing through that fiber, whereas with single mode, only single. And you'll see here that the core is much wider. Since the core is much wider, though, it means that we don't have the extreme distances that we would have with single mode fiber. So what you'll do is you'll typically end up using multi-mode fiber when you're connecting your switches to your switches or your switches to the routers, and you'll save single mode fiber for extremely long runs of optical fiber laying, if you must. Now, notice that this image here, the cladding, or not the cladding, but the cladding in the core is the same height. You might be saying, well, that's so you can, keep your image nice and linear, right? No, not at all. Not at all. We have a standard size for the cladding and the core combined. And that standard size is 125 microns. So no matter the size of the core plus the cladding is going to be 125 microns. And then our overall size here you can see is 250 microns once you add the buffer or the coating on top of it. So the buffer, the coating is there to protect your cladding. It's there to protect your core from scratches, from breakage, and so on and so forth. So, but regardless, that cladding and the core are going to be combined 125 microns. So if we go back here to this image, with a bigger core, we have less cladding. With a smaller core, we have more cladding. So single mode, as I said, we're going to use lasers, but multi-mode, we're going to end up using LEDs for our light source in those cases. You'll notice here that the 9 micron core, that's for single mode fiber. And if you're thinking, whatever, micron. What do you mean by micron? Well, it's very small. Here's something you can think about. The average hair is about 50 microns. So if the average hair is 50 microns, then we're dealing with something that's thinner and smaller than the average hair. That's what we're dealing with. Your multi-mode is going to have a bigger core than 9 microns.